our analysis. So as you can see, if I increase this value, the points get away from each other, right? And then you can see that at the next bifurcation point, which happens around 3.4 something, it's the same story. Okay, if you remember, in the previous bifurcation, this was -1, and the second order function's derivative was 1. This time, f2 is -1, and f4 is 1, and there is another bifurcation. And if you can see it, this function looks awful lot like itself. Do you see it? Some fractal stuff coming your way really fast. So how does it look like itself? Imagine this whole function, and then just take, you see this goes up, then there is this castle here, right? And then if you look here in reverse, it goes up, then there is a castle here. Do you see that? Yeah. So it's as if this function is itself, but shortened, rotated, put it down, right? Self-similarity. So
this looks an awful like what's like the truncated Fourier series of a step function.
What step Fourier function?
Truncation. So taking the finite, it's almost like we have taken just the finite in terms of Fourier series of some complicated step function.
Ah, I see. Very good, very good. What was this one? Okay, I will come to that one soon. Well, as I mentioned, we do understand why those periodic windows appear. They appear, for example, if you plot f3 versus x, the period 3 appears when the function just barely touches this line, okay? And you might think that finding this is very easy. Actually, there's a story here. One can show analytically that the value r at the tangent bifurcation is this. So when r is 1 plus square root 8, you have that period 3 window appearing. This beautiful result is often mentioned in textbooks and articles, but always without proof. Given the resemblance to this result, that is for another thing, I'd always assume it should be comparably easy to derive, and once assigned it as a routine homework problem. Oops. Turns out to be a bear. No, okay. There's bear with me, there's the beer, there's the beer, I don't know how to read them. But in any case, this is also is a part where you have this intermittency, meaning that things go rather in an ordinary way, except for some burst of activity in between. So that's another way of going towards chaos. It's called intermittency route to chaos. But we will focus on period doubling route to chaos. What do we mean by that? Let me just find the relevant place here. Okay. So, it turns out that there is some mathematics, some geometry hidden here. Let me show you how. You have a bifurcation here, right? The next bifurcation is here, the next bifurcation is here, the next one is here, and they get closer and closer, right? So Feigenbaum realized that if you take these distances, like between the first bifurcation and the second bifurcation, let's call it delta n, And let's say the second one and the third one is delta n plus 1. And if you take delta n over delta n plus 1 and take limit n goes to infinity, meaning that it bifurcates smaller and smaller, smaller and smaller, smaller and smaller, it converges to a universal number. Okay, magic. Let me remind you, we started with a simple function, lambda x 1 minus x. Then we saw bifurcations, we were surprised. Now we are seeing that there is some geometry hidden in that bifurcations. And this number has nothing to do with e, pi, or any mathematical constant that we know. It's another mathematical constant. It's a mathematical constant of chaos. Okay? Why it's a mathematical constant? Because, as you will see in your homework is to look at this map, okay, and change mu. So you will see the same kind of bifurcations while you change mu. Of course, the values of those bifurcations will be at different points. But you will, if you do it correctly, you will see that as you get closer and closer to bifurcation point, the chaos point, the points where that bifurcation happens, if you take the ratios, it converges to the same exact value. So a different map. And it turns out that as long as you have one hump on your function, and as long as that hump is quadratic, you will get the same values. Okay? That's not where it ends, though. There is another universal constant, and let's define it like this. This is the maximum point of the plot, okay? The maximum point of the plot. Over here, x maximum. If we look at the distance from this point to the closest bifurcation point, okay, do you see that it gets smaller and smaller? But it also alternates and gets smaller and smaller. Now, if you do that one, dn plus 1 over dn, as n goes to infinity, you will get another universal constant, etc. Now we will derive these constants and we will try to understand what it is all about. Okay? Okay. So let me first we will come to that point. Let me first tell you where that there is an encyclopedia in the internet, the online encyclopedia of integer sequences. Okay, a lot of fun. So you can find pi here or other stuff like that, but this is a sequence 3.5699456718 etc. What is this? This is the point where all those bifurcations approach to, you know, period double, double again, double again, double again, double again, until you hit exactly this point where you exactly start the chaos. And we will be able to exactly pinpoint this point of chaos with some methods, okay? But let's say we did it. Let's say we know the number, infinitely many digits of it. Let's actually plot our function as it goes closer to it. And I'm going to plot, let me gather my thoughts together. What I have here. This one, this one, this one. Let me just plot it like this. Okay, this is already ruining the surprise. So give me a moment to think. Okay. Okay. I thought about it and I'm plotting it again. I will explain. Everything will go right. Just wait for this plot. Okay, here it is. Now, what is nice about this plot? You see, with this plot, we had to zoom in, and every time we zoomed in, we have lost the quality of the plot, right? You remember that. Now, what we are doing instead is we know where it hits the cows, right? So we are approaching that point logarithmically, meaning that the x point is minus of the logarithm of r critical minus r. Who can explain me what is going on here? Anyone? So what is 0 here? RC minus R equals e to the power of 0, right? Yes. Very good. 2 means RC minus R is equal to e to the minus 2. This one means RC minus R, so we are really, really close, but as we get closer, we approach slower. So the fact that these distances now seem to be equal is just telling us that our approach is geometric. Okay? As you go closer and closer, you have to travel the same amount of distance in the exponential to get to the next bifurcation. Now I should be able to zoom. Okay. If I zoom here, you get the same story. Zoom here, you get the same story. Zoom here, you get the same story. And this distance over here, from here to here, what is this distance? Can you tell me? Approximately. 1.6 or something like that, right? Let's do MP exponential 1.6. Do you see? It's very close to the universal constant, 4.669. Do you understand it? Do you understand why this is the case? No, right? Okay. Let me explain. This is RC. This is the way that we see this plot, right? So let's say this is Rx. No. Let's say this is, what was it? 9.8, right? This is 9.8. And this point is what? 8.3. Okay, so it is telling you that the ratio of this one to this one is, so one of them is R, let me just call this one R1, R2, R3. R1 is equal to RC minus e to the minus 8.3. R2 is equal to RC minus e to the minus 9.8. R3 is equal to RC minus e to the minus 9.8 minus 1.5, which is what? 11.3? Did you follow this? Yes? So what are we looking for? We are looking for R3 minus R2 over, I have to be careful. Is this what we are looking for? No, we are looking for R2 minus R1, R3 minus R2. I think this is better. Please help me out. No one is going to help me out?
No, I think the above one should be reversed. It should be e to the minus 9.8 minus e to the e.
Look, hear me out, hear me out. Do you agree that this is much smaller than the other one? This is much smaller than the other one. So if you divide them, it's approximately e to the 1.5.
Yeah.
That's what's going on. So
You don't even need to approximate. In both cases, we can factor out.
exactly,
Yeah.
exactly. You can factor out 1 minus e
Yeah.
to the power of something, and you are going to exactly get e to the 1.5. Are you happy? Yes, good. So this distance tells us something. So that distance tells us the first Feigenbaum constant. Actually, people call it Feigenvalue. Okay. I'm glad that you smiled at least once during this course. So we got the idea about first Feigenvalue. What is the intuition for the second Feigenvalue? So if you remember, it was the distance from the maximum of the plot. So let's do the following. The maximum of our plot is xm equals to 0.5. That's where it's maximized. So I'm going to plot. Let me plot not the logarithm, just absolute value first. Just absolute value of the axis. Okay. Do you see what I did? Whenever it's below 0.5, it's flipped up. Yeah. Okay? Now, do you see this point?
Now there is also self-similarity here.
Exactly. Now there is a self-similarity. You can see this plot is basically this plot, basically this plot, basically that plot. But it's getting smaller and smaller, shrinking. So the point where we are going to concentrate is these points. Do you see this point goes down, then goes down by a similar amount, right? So if I plot it in log, again, also that axis, it's going to be cool. Okay, let's do that in log. And I have never seen anyone plot it this way. So you don't feel it right now, but you are really lucky. There you go. Now you have one plot which is in log, and it has both Feigenvalues in it. The first Feigenvalue we already discussed corresponds to the distance between this point and this point. And that's around 1.5, and that corresponds to 4.69, whatever. The second Feigenvalue is the distance in the vertical direction. So this distance, this one with respect to that one. Because remember, if it was going down logarithmically, and I plot it in logarithm, so it now goes down linearly. Sorry, it was going down exponentially. I took the logarithm, so it now goes down linearly. Well, how about these numbers? What is this number? 7.5 something. Let's just focus. 7.45. Remember that. Now I go to the next one. Okay, sorry. So 7.45. What is this one? 7.45. What is this one? 8.35. Something like that, right? 0.9. Okay. Okay. It's very close to 2.5, right? But we will get so good at it that we will eventually get all the digits. Do you see? Very nicely. Let's get super good at it. Let me show you the final code. For final code to work, I actually have to go to higher precisions in decimals, like to 32 precisions. What this code is doing is finding the precise position of the bifurcations and finding the distances. And if you run this code in 38 seconds, it finds the relevant Feigenbaum constants. You can see it goes closer and closer to those values. And what we are using here, have you heard of binary search?
Yes.
Yes? One thing that we are using is binary search. But I have to explain you so many things for it to make sense. Okay, let me think. So here is how it starts. R1 is 3. Do you remember 3 was the first place where it bifurcated? Where do we expect the next bifurcation to happen? We expect it to happen. We don't need to expect it. We actually find it by this function, find bifurcation point, and we are just giving it where we expect it to happen. We expect it to happen between 3.4 and 3.5, okay? And it finds that value exactly. Now, how does it do that? If we go to find bifurcation point function, this is how it works. And find bifurcation point actually depends on derivative at fixed point. And the derivative at fixed point depends on finding fixed point. And this is find fixed point function. Are you still with me?
No.
Inception. Come on, you don't need to do that face. Okay. Let me give you, this is too hard, right? Okay, let's go back to some concepts. I will talk about something very important. This is Lyapunov exponent. So let's go back to our book, talk about Lyapunov exponents. Where is it? Oh, I have also renormalization. So much fun. Let me talk about. Alper, do you know this stuff?
Which one?
Like, for example, Lyapunov exponent.
I have heard of it, but not much.
Okay. So this will help. Just trust me with this. Okay. What is Lyapunov exponent? Lyapunov exponent tells us whether we are in chaos or not. Okay? Here's what it means. Let's say you start at x0 and you have a tiny bit of delta 0 here. Okay? So basically I'm starting at x0 and I'm also starting at x0 plus delta 0. Okay? If I am at chaos, chaos means sensitive dependence on initial conditions. Okay? So it means that this one, if I am at chaos, this one will go its own way. This one will go its own way. At some point, they will start to diverge. Let me just plot them together. Like I start at x0 and it goes like this. Okay, I start at very close here. At first it's together, but then it deviates and there's no interaction between them anymore. So that's when it's at chaos. When it's not at chaos, this is chaos. When it's not at chaos, let's say x0 goes like this. x0 plus delta x0 will go like this, and it will converge to the same points. Yes? So Lyapunov exponent is defined in this way. Let's say you have delta n, which is like you start with x0 and x0 plus delta 0, dot 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 xn, dot 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 xn plus delta n. Okay? If magnitude of delta n, let's say that magnitude of delta n and over delta 0 is approximately e to the n times lambda. Okay? If lambda is positive, then it's exponentially increasing, right? If lambda is negative, then it's exponentially decreasing. Yes?
Yeah.
So we will actually pinpoint exact position where chaos starts by calculating Lyapunov exponent for our map. Now, when it comes to our maps, they are like this, right? 1D maps, they are like this. So I have already said that this is how Lyapunov exponent is defined. So you can write lambda as 1 over n times ln delta n over delta 0. Do you agree with that? Yes? Now, what is delta n? It's fn xn, sorry, fn x, it's what is written here. I'm trying to write the same thing again, but it's written here, right? So what is it like? It's very familiar to you, right?
Derivative.
It's the derivative. It's the derivative of nth iteration of the function. But derivative of nth iteration of the function, in our case, has a very special meaning because, you know, f of x0 derivative is just f of x0 derivative. But if you have f of x0 derivative, right, you can write it like this: f derivative f x0 times f derivative x0. Do you understand this? But what is this fx0?
x1.
fx1, right? So you have fx1, f derivative x1, f derivative x0. If you want to go further, f derivative x2. If you want to go further, f derivative x3. Do you see it?
Yeah.
So fn derivative is just multiplication of fn minus 1, sorry, f prime xn minus 1 times f prime xn minus 2 dot 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 until f prime x0. Does it make sense? And this multiplication, when you take the ln, that multiplication becomes a summation. Do you see it? So to find the Lyapunov exponent, what you need to do is, I give you a function, and I tell you, find the Lyapunov exponent at this point. What do? You basically find x0, x1, x2, x3 by mapping, right? By playing this game. And then you find the derivatives at those points. Then you take their logarithms, then you sum them up. Okay? Now, what is nice is if you do this for the logistic map, I hope this is for the logistic map. Yes, it is. Something very interesting happens. Do you remember the bifurcation where they were? There was a bifurcation at 3, and then there was a bifurcation around 3.4. Then there was a bifurcation around 3.5. So at those points, Lyapunov exponent is exactly 0. Do you see? 0, 0, 0. So Lyapunov exponent goes to 0, hits it, comes back down, hits it, comes back down, hits it, and starts hitting faster and faster as it approaches chaos. And right at chaos, it goes to positive. Okay? So it's a very good tool to find exactly where the chaos starts. Okay. I think this is the picture for the Lyapunov exponent as we approach the chaos. So let me run this. Let me interrupt and run the easier one, the one that is understood in an easier way. Okay, this one. Come on. I think I have a new Mac, and in that new Mac, these things run faster, and I presume that they will run faster here as well, but they don't. So what I'm plotting right now, it's not plotting, so let me, okay, here it is. Yeah. Again, the same idea. Just ignore this. It's logarithm minus logarithm of RC minus R. Do you remember? So we are getting closer and closer. And as you can see, Lyapunov exponent goes to 0, hits it, comes down. Hits it, comes down, hits it, comes down. And it will actually go to plus after some point. Okay? So I can find exact position of critical point where it turns to positive by binary search. Let me explain what binary search is for those who don't know. So what do I expect? I have this Lyapunov exponent, and when I hit RC, over here it's negative, and sometimes it goes to 0, etc. Here it becomes positive. Okay? So here's how binary search works. I start from point A and B, and I look at the middle point. So I start from point A and B, and there is the middle point over here. So if this point is positive, remember we are looking for 0, right? So if this point is positive, then I switch B to be that point. Why? Because I know that the point where it hits 0 is somewhere between these two. Does it make sense? Yes? Yes? So my new AB is here, AB is here, and I calculate it at midpoint. Let's say it became negative. What do? A is now M, right? So I go closer and closer to determining where I hit 0. Okay, exactly. So we can analyze this code. This part is calculating Lyapunov exponent. How does it do it? It first iterates it for 2 to the power of 15 steps. Then starts calculating Lyapunov sum, which is logarithm of the derivative of the logistic function, listen carefully, you will do this for sign map, okay? Or you won't. And this is the binary search. Lower bound, upper bound, and you go between bounds, you find the middle point. If it's lower, you shift this one, etc. So I know that the critical point is between this value and that value. So I run this code, and boom. Estimated value is 3.569945, and exact value is 3.5699, etc. Difference from exact value is 10 to the minus 14. Yes? Yeah. I forgot to talk about renormalization. Can you handle it? Why not, right? Why not?
I don't think we can even handle these by ourselves.
No? Should I stop? Is it important? Is it important for homework? It depends how you decide to do the homework. But you can do the homework with what I have already explained. Renormalization is super, super cool.
Let's see it.
Let's see it. So what Feigenbaum realized is that, let me go to here. Let me go back. Back here. Let me just run this one more time so that it's not glitching, hopefully. Okay. So 2.9, etc. So I'm going to do something. Please watch carefully. Okay. So look at this second F2. Look at F2. Do you see this function like this? Do you see over here? Just print that image to your mind. Okay. Now I go further to F4, and when that function comes back to the center. I'm sorry about these glitches. Now look at F4, which is purple. Do you remember the previous one? So now F4 is the same one but flipped down. Okay? So that's the renormalization. Feigenbaum realized that if you plot this at R0, this is, I presume, is R0. If you plot fx at R0 and then you plot it again f squared at R1, this picture looks very similar to this picture, but only reversed and stretched out. Let me give you another example. This is fx0, this is f squared x at R1, and this is renormalization. Alpha times f squared times x over alpha times R1. I mean, it's the same functions. It's f of f, but stretched, x over alpha, and multiplied by alpha. So he realized that this stretching and this stretching is the same. Okay? And this is just going from R0 to R1. We went from R0 to R1. Then if you do it for R2 and if you do it for R3 somewhere here, these R's are getting closer and closer, right? So he realized that actually at infinity, when you hit chaos, it's more or less the same R. So more or less we are dealing with a function that is self-referential. Fractal stuff. So this is the universal function. No matter what you do, whether you are doing a logistic map or sign map, doesn't matter. Given that you are dealing with quadratic function, unimodal quadratic function with one hump that is quadratic, you will arrive at this function. That's the universal function. So let me do a very simple mathematics to get an idea for alpha. Are you with me? This will be very easy. So let's say g of x is 1 plus c 1 times x to the, let me do it c2, x to the 2 plus higher order terms. Let's say that's how the function is, okay? If I'm going to reach here, then what do I need to have? I need to have 1 plus c2 x squared equals alpha times g of x, which is 1 plus c2 times 1 plus c2 x over alpha squared done. Do you agree? Yes? Look what happens. 1 plus c2 x squared is equal to alpha plus alpha c2 plus, help me out. Did I make a, yes, alpha c2 again?
Alpha c2 square,
I think so too. You are not sure? Let's go step by step. Alpha times 1 plus c2 times 1 plus 2 c2 x squared over alpha squared plus something of order x to the 4, right? And we don't care about it. So far, how are we doing? Are you sure?
No.
Very good. Alpha plus, what is square? C2 squared? Nothing squared, okay.
I said 2 was square.
Yeah. And this was just one. Imagine going C4 x to the 4. It's not there. Alpha C2 plus, I have 4 minutes. Alpha times 2c2 squared over alpha squared x squared. Yes, very good. And order of x to the 4, we don't care about it. Look at this. 1 is equal to alpha plus alpha c2. That's equation 1. 1 equals to alpha times 1 plus c2. The other equation is c2 is equal to this thing. Do you see it? C2 is equal to 2c2 squared over alpha. So far, so good? We don't care about, okay, one solution is C2 is equal to 0, but then alpha is 1, but we don't care about that solution, okay? The other solution is when 1 is equal to 2c2 over alpha, which is 1 is equal to 2c2 times 1 plus c2. Do you agree? Because alpha is 1 over 1 plus c2. So far, are you still with me? So what do I get? 2c2 squared plus 2c2 minus 1 is equal to 0. Right? What is c2? Minus 2 plus minus 4 minus 8 plus 8 over 2a, right? Which is 4. C2 is minus 1.5 plus minus square root 3 over 2? Over 2. We are going to use, we are almost there. Alpha is 1 over 1 plus C2, right? So, which one should I use? 1 over, let me use this one. It will be back, don't worry. When it is back, you will have the solution. 2 over minus 1 plus square root 3. In any case, this gives you minus, I think, sorry, 1 minus square root 3. This gives you minus 1 plus square root 3, which is around minus 2.73. Do you see we got alpha, which was 2.502. Do you remember? It's 2.503. We got a nice approximation for it, and this is where we can stop for now. Let me ask you, should we continue with this stuff or should we start a new chapter next time? Did you get the message? Bifurcation. What I didn't mention, just give me 1 minute to mention this. What I didn't mention is that this bifurcation will later appear in actual systems. Like there are experimental tests, there is a system, and the system starts going like A, and then becomes A, B, A, B, A, B, then becomes A, B, C, D, A, B, C, D, A, B, C, D, something in the system. Like there is a period doubling that appears in actual hydrodynamic systems, like economic systems, whatever systems. Take care.